We're up to now almost 100 times overall average improvement over the course of a 700-kilometer flight. It's the first time in any navigation application that this has actually worked. Q-Control's core value of being real, another one is to be revered. That means that we can't just do demonstrations that something happened. So in this case, the navigation solution gave us positioning estimates that were better than the best GPS alternative.
Did you know there are over 1,000 GPS denial attacks a day around the world? If these attempts succeed, a plane or other vehicle could experience everything from a nuisance to a disaster. Can quantum technology help? We dive into cutting-edge innovations in quantum sensing, exploring how it's revolutionizing aerospace and defense in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our repeat guest today is the CEO and founder of Q-Control, Michael Biercuk. Welcome back to the show.
Thanks for having me.
Yeah, it's been over 3 years. It's been a while. So there's a reasonable chance that a lot of people listening didn't hear the last episode. So
it's a good thing both of us survived. So.
Yeah. So I'll give you a chance now maybe to just introduce listeners high level what Q-Control is in case they're not familiar.
Sure thing. Q-Control is a company I founded in November of 2017. So we've been around coming up on 8 years, which is amazing. Focused on how we can make quantum technology useful through software, and in particular through AI-powered infrastructure software. So there's been, as many people in your audience will have heard, a huge amount of discussion about the convergence of quantum technology and AI. But this goes well back in history before the current surge linked to large language models and everything we've seen with OpenAI and the like. We have, for the entire arc of our existence, focused on how new kinds of AI and machine learning could give us access to the quantum world in a way that is better than what we can do with our grubby human hands. Using intelligent machines in this way has enabled us to build new kinds of capabilities in both quantum computing and in a new area, quantum sensing, that have really pushed ahead in what is possible in the field. So in quantum computing, we build what's called performance management software that makes the computers thousands of times better. And in this other discipline, quantum sensing, we also focus on software level innovation, but here leveraging AI-powered software not only to automate the hardware, but also to make it more resilient in real world environments. So it can give us the insights that we care about and not just be swamped by interference.
Great. And before we dig into part of what you're doing that made some news recently, I have a question for you. So I remember you've been doing the AI approach here to how it can interact with quantum for a while. Normally when someone says when quantum meets AI, like when they say that now, it's this kind of like crazy hype thing. Like they're imagining that you're going to put an LLM on quantum and it's going to be awake or take over the universe or something like that, right? So how does that make you feel when you hear that? Because for you, it means something very, very different. And that said, is there some future hope you'd like to see with AI and quantum coming together too?
Well, I think the challenge that I observe and that maybe my colleagues observe is that aspiration, that new forms of quantum technology will allow us to build new forms of AI that are more powerful or whatever. That is bandied about with very limited substance behind it. It's not the idea that the aspiration is bad or even wrong. It's that there's almost no substantiation. And so we, as an organization whose first core value is to be real, have focused on the real, true, deep applications that come at the intersection of AI and quantum. And for us, that's AI for quantum, as opposed to quantum for AI. Right. That's what most people talk about. Now, I have to say, it remains very interesting in the medium and the long term to think about how using AI for quantum leads to new quantum systems that feed back and give us potentially better AI in the long term. However, our focus right now is ensuring that we build this very solid technical foundation on AI for quantum to do things that have just never been possible before.
Okay. So do you have like a dream use case then for maybe into the next year that you'd like to see AI help for quantum computing?
So in AI for quantum computing in particular,
Mhm.
we remain deeply focused on this challenge of dealing with error and hardware instability. And we've been focused primarily on two core technologies, one which everybody's heard of called quantum error correction, which is relevant in the long term, but another that is secretly the thing that actually makes quantum computers work. That's called error suppression. If you want to be pejorative about it, it's really just operating the hardware correctly. It's doing it in a way that is less susceptible to error, leveraging the insights that come to us from intelligent machines, from using AI technologies. Now, we are, of course, investigating end use applications, not just the middleware or the infrastructure software that we build. And we've actually gotten quite bullish on the idea that in the near term, the next maybe 2 years, if you'll permit me to have a 2-year horizon instead of a 1-year horizon,
Sure.
in the next 2-ish years, a series of problems in a decidedly unsexy area of logistics optimization and transport optimization actually look like they will be addressable with quantum computers in a way that is better than the best conventional alternatives. That is the onset of quantum advantage. Now, I know this is a topic of huge discussion and debate in our field. We've approached it a little bit differently than others. Instead of thinking about what happens when you build an asymptotically large quantum computer or a complexity theory argument, we focused on the more practical challenges. Where are there problems that are amenable to quantum computers? Where are those problems underserved by existing technology? And where are those problems high value? And when you take the three of those together, there's a very narrow range of opportunities that we've identified, but the threshold looks to be much closer than we perhaps considered 5 or 10 years ago. And it is the AI-powered infrastructure software that pushes us over the edge in terms of delivering the performance needed to make those applications real. So just recently, we set a world record for the world's largest what's called constrained optimization problem. It's a very specific math problem that's relevant to how you make the timetable for trains. Turns out it's an extremely hard problem.
Mhm.
And with this new technology we've built, we can really push the limits on the machines, and we think we're getting really close.
I live in New York City, and I can promise you they still haven't figured out that problem here.
It amazes me, right? Aside from the jokes that we all make about the cities in which we live and the shoddy transport networks, even though it seems easy, right? The trains stay on the tracks. It's not infinite degrees of freedom, if you will. It turns out that rail is one of the harder optimization problems because it's so constrained. In fact, the fact that it's stuck on the rails means that you have less ability to optimize. And the number that I came across in the technical literature is even with modestly sized rail networks in a lot of major cities, you can only approach the actual optimal solution within about 50% because it's just too hard mathematically. Anything on top of that is a win. I guarantee if you get 5 minutes back on your journey, you're personally going to feel gratified, even if it isn't a computational complexity theory, asymptotic exponential win. Those 5 minutes matter to you. They matter to your family. And so we focused a lot on problems that have that kind of characteristic.
So with a good amount of error suppression, obviously less error correction might be needed. Hope that's the hope, right?
Indeed. So right now, we even think that quantum error correction will not be required for these initial problems. In the medium and the long term, it clearly will. There's no doubt. But we've also been exploring how what we call quantum error correction primitives, that is bits and pieces of error correction without the full shebang of logical encoding and syndrome detection, all those things, can actually make the machines more useful today. And it's this combination of the AI-powered infrastructure software and error correction primitives that, in another example, let us set the world record for the largest entangled state ever realized. It's a 75-qubit GHZ state with verifiable entanglement on an IBM processor, and it comes because of our software. So less requirements on QEC, pulling little bits and pieces out of QEC, more AI-powered error suppression. All these things together are what we think push us toward the edge of quantum advantage in quantum computing.
And before we leave this topic, Is it just transmon that as a modality for this application, or do you see it in multiple modalities?
No. It's first of all, our technology is completely agnostic of the underlying platform. Of course, we tailor it to the dominant noise processes in a trapped ion or whatever. We recently announced an integration of our software, which is called FireOpal, with IonQ. We have partnerships in the background with a number of companies in different technologies. We announced a partnership, an integration last year with a company called Dirac, which makes semiconductor quantum dots. The simple reality is that the commercial systems built by IBM and peer companies like Rigetti and others are simply more advanced today. We make no statements about who will be the ultimate winner. We're like the quantum Switzerland, if you will. But we've used what is available, and we can actually just make it do outrageous things.
So your goal then is to have that available to anyone who logs in on the cloud, for example, and wants to run a quantum computer. They're going to get that extra performance basically built in.
Absolutely. And I think you touch on a really important subtle point that most of what you read about, if you're interested in quantum, if you're adjacent, if you want to be an end user, most of what you read about is completely inaccessible to you. It is just a research demonstration that a company or an organization has done in the background using their own internal tools. And they either have no intention or no ability to bring that commercially to market, right? Many of the demos we hear about are really science experiments. Not all, but many. We, as a product-focused company, have worked very hard to ensure that everything we build is actually usable by an end user and actually delivers net improvements. Not in this one narrowly isolated use case, I can get an advantage, and in every other edge case, it totally collapses. That is not a product that is useful. So it's important that the way we deploy our technology is as a commercial product that looks to deliver real value to end users and not purely a science experiment.
So hopefully another piece of that stack that whether users understand it or not is helping their lives.
That's right. I mean, look, all of us every day, right now we're using a cloud-based platform for doing this recording. We think about the interface. We think about the particular platform you're using now, or Google Meets or Zoom or whatever. But what we don't think about is that in the background, there is a huge swath of infrastructure software that's running and making those cloud assets, the cloud computing hardware, actually useful. One of the most famous is VMware, recently sold for $75 billion. And I guarantee most people in your audience don't know about it. It is, however, what makes everything work in the background, and Q-CTRL and our AI-powered infrastructure software for quantum computing plays exactly the same role.
Yeah, almost nothing runs on the metal, and people don't realize that.
Exactly.
Almost everything is virtualized to some levels. You can blow it away and bring it back. And
exactly.
Yep, that's great. So now we're going to get to another topic that in some ways is very timely. If you think about the last couple of years, air travel has been wild. Like it's kind of all over the place what's been going on with the challenges. And one interesting challenge now that could potentially face it is this idea of some kind of denial of service of GPS, right? In some way. Can you introduce listeners to what that might look like just first before we talk about what you're doing about it?
Sure. Again, another thing that has become so ubiquitous we don't think about it is GPS. We use GPS for pretty much everything we do. We use it when we walk around and use Google Maps to try and help us find where we are relative to some bar. We use it when we get in an Uber, and we use it when we get on an airplane. Airplanes generally rely on some form of GPS-based navigation to help ensure, at least through part of the flight, that they are on track, not straying into exclusion zones like near the White House, et cetera, right? GPS is very widely used in aviation. And what we have seen, not just in aviation, but broadly over the past 5 to 8 years, is a huge uptick in economic and strategic sabotage of GPS. We see it from state actors. We see it from non-state actors. We see it in commercial shipping. We see it in aviation. We see it in ground-based things. Basically, GPS works like a radio receiver. You have a little instrument that picks up a signal from a satellite. And it's not very hard to disrupt. All you have to do is broadcast a stronger signal that's nonsense, that's interference. And you can buy a GPS jammer for a few $100s on Amazon. It's often illegal to use, but it's very easy to get your hands on. As a result, there's been this huge proliferation. And then as we've seen a rise in geostrategic tensions all around the world, we've now seen more active, high-level, massive disruption. So starting in March of last year, March of 2024, I'm going to tell you something that's going to horrify you. I'm sorry. Starting in March of 2024, we went from a small number of reported GPS denial attacks on commercial aircraft, dozens a day or something, all over the world, to more than 1,000 a day. And this comes from the automated transceivers. It's called the ADSB on the aircraft, right? It just says, oh, we have a problem. We lost GPS signal. It's being actively denied, or it's being spoofed. We're getting a fake signal that tells us we are somewhere where we aren't. And it's gotten so bad that in, I think, April last year, there was a case where a Finnair flight was trying to land in Estonia from Finland and had to turn back because it was suffering GPS denial attacks. You also saw this tragic case of an aircraft near the Ukraine conflict zone that strayed into restricted airspace because it was suffering from GPS denial. Seems like it then was attacked by Russian anti-aircraft artillery and later crashed. This can have real impacts on flight operations, because obviously you want to avoid those things, but also flight safety. This has become one of the top strategic concerns because it's not only in commercial aviation. Think about any aviation, whether it's crewed or uncrewed, defense or civilian. GPS denial is a new weapon that's being used very widely.
And you literally never hear about this. It's kind of crazy, right? There have been a few disasters recently, and you hear that, the thing that caused that disaster happens however many times a day, and you just don't hear about it. And that's terrifying, like near misses, whatever. And now we've got this that's exploding, at least hopefully not literally all the time. And no one hears about it, right? I can't remember the last time I was listening to the news and I heard them talk about GPS denial attack. It's just not ever mentioned. And it sounds like it could be one of the most critical types of attacks. So we had Boeing on a couple of years ago, and they were talking about working on something, I think, similar to what you did, where it was this idea of like a GPS kind of gyroscope, a quantum gyroscope sort of with sensors to help you figure out where you are, like keep you on track, that kind of thing. So has this built on that work at all? Is it related to it all, or is what you did completely different?
So the first thing is to say is yes, Boeing, many other organizations have been focused on whether quantum technologies can provide backups, new kinds of navigational resources that help when GPS is not available. Mm-hmm. At Q-CTRL, we have 3 separate programs that are all linked to making new kinds of what it's called alternative navigation. Now, it's important to say, there was a time where we navigated before GPS. And as a result, there are lots of existing alt-nav technologies, backup technologies. The simple fact is they're not that good. Right? They tend to suffer from errors that accumulate over time. So if you have a very long flight or a very long mission on the sea or undersea, the errors gradually creep in. And after not too long, you're way off from where you think you are, where you think you should be, excuse me. We set out to build several different kinds of quantum assured alternative navigation. I'll tell you the 3, and then I'll tell you the one we really focused on. So First is what's called a quantum inertial measurement system, inertial measurement unit. This measures motion, it measures acceleration, like the device in your phone that makes it rotate when you twist your phone. That kind of device can be used to pick up the vehicle motion and then, using Newton's laws, basically, integrate over time to figure out where you are if you knew where you started. Quantum inertial navigation. We announced a partnership with Lockheed Martin, and we won an award from the U.S. Defense Innovation Unit earlier this year focused on quantum inertial navigation. But there's a whole nother approach, because the thing about quantum inertial nav is that it suffers from this gradual accumulation of error. You can make the accumulation slower using quantum technologies, but it still accumulates. The alternative is something based on what's called position fixing. And it harkens back to something many of us may have experienced as kids, or at least we were adjacent to it. It's called orienteering. Orienteering is a game, if you haven't heard of it before, where you're given a map. And of course, you have your eyes. You're dropped somewhere you don't know, and you're asked to navigate to a target destination. And in orienteering, what you're doing is you have a reference, a map. You use your eyes as sensors, and you say, well, I see a hill, I see a valley, I see a river, and that means I believe I am here on the map. I can position fix based on the landmarks that I see. Now that works pretty well, actually. There are very good vision-based systems for aircraft, crewed and uncrewed, that take pictures of the ground and compare to a map. But what if it's cloudy? What if it's dark? What if it's over featureless terrain? Those systems no longer work. You could also shine a laser into them and disrupt them. So with quantum technologies, quantum sensing technologies, we gain a new set of eyes that allow us to see the world in a different way. Instead of seeing the terrain, the bumps and wiggles on the surface of the earth from hills and valleys, we can see the terrain that comes from other geophysical signals, like fluctuations in Earth's gravity, or in the current demonstration, fluctuations in Earth's magnetic field. Now, we typically think about Earth's magnetic field as just pointing north, giving us a direction. But it actually has all sorts of little bumps and wiggles that are a unique signature linked to particular locations based on what the crust is composed of, right? So this is the so-called crustal anomaly field. And for decades, mining companies, defense organizations have made maps of this stuff because it's linked to what's underground. We all want to know what's underground. What we did was we built a new magnetometer that allowed us to see the tiny little bumps and wiggles. And these are quite small relative to Earth's overall field, the one that points north. Built a really high sensitivity, really high stability magnetometer, and combined that with these novel approaches in physics-informed AI to allow us to pick the signal out of the huge noise interference that we get, because we're putting these things on vehicles, on airplanes, on boats, on ground vehicles. And if you just think about it, you're putting a metal airplane with all sorts of electronics and big spinning turbine blades and stuff, or propellers. You're putting that in Earth's magnetic field. It's a huge source of noise, of interference. So what did we do? We took our full stack system, which includes our magnetic denoising, our map matching algorithm, our magnetometers. We flew it, and we performed positioning. We asked, based on the sensor's inputs, where are we likely to be relative to a publicly available map? Nothing special. We didn't get some secret defense information. Just downloaded a map off the web, and it worked. And it worked much better than the common alternative, which is called the strategic grade inertial navigation system. It's the backup that exists on basically every aircraft. We used a very, very high-end one. We showed in our technical manuscript that we could do about 50 times better than this best GPS alternative, like for like. It's the same, approximate size, same approximate power, also unjammable, unspoofable, etc. So it was a huge thing. Now, since then, we've done even better, right? We're up to now almost 100 times overall average improvement over the course of a 700-kilometer flight. So very long flights, many hours. And it's the first time in any navigation application that this has really actually worked, that it's been better. Not that it gave some signal, right? Again, coming back to Q-Control's core value of being real, another one is to be revered. And to us, that means that we can't just do demonstrations that something happened. It actually has to work. So in this case, the navigation solution actually worked. It gave us positioning estimates that were better than the best GPS alternative. And in the best case, brought us within 22 meters of the actual true position given to us by GPS over a roughly 500-kilometer flight. Now, it wasn't always that good. It depends on where you are and how the airplane is flying and whatnot. But it's the first time we've ever seen this kind of quantum advantage in a real application like this.
So to clarify for listeners, when you say better than the other alternatives, do you mean better than classical, like gyroscope kind of thing that continues to guess where you are, or like a quantum sensing one?
Better than the currently deployed classical inertial system, right?
Okay.
So these things are really good. I got to be clear. This is not an easy thing to beat. So that's why we set out against the highest end one, the strategic grade. But that is the kind of device that's broadly deployed in aircraft and other vehicles. We compared head to head against that. There was a very frustrating AI generated third-party content aggregator that misrepresented our work. We, just to be clear for your audience, we're not claiming we're better than GPS. We're claiming we are better than the GPS alternative that you have to rely on right now if GPS goes out.
And is this available everywhere? So you mentioned that mapping that AI uses and everything. Are there maps literally the entire world, or like in some regions will it just not be as effective because we don't have the magnetic densities and all that?
So there are two important points here, right? One is map availability. There are global maps, but they are not uniform quality over the world. And so there is a definite drive to get better maps. There's no question. I want to emphasize, we only use publicly available maps. So anybody who has a baseline feeling that, oh, this can't work because the maps aren't good enough. Well, it worked, right?
With publicly available
Can it
maps,
work? Can it work anywhere? This remains to be seen. We think there's a need to have much better maps. And if you think back in history, think to, I'm old enough to remember MapQuest, right? When MapQuest first came out and you get these maps that are barely any coverage. And now you think about Google Maps with Street View, where you can actually see inside the restaurants and the bars that appear on the map. That's been driven by demand, right? Customers wanted more information. And so more data was collected for the map. We think the same is going to be true here. Now, the other part of your question is really about the quality of mapping and can it be used in all domains? And we know it works pretty well over land because Earth's crust is at the surface. That's at 0 altitude or whatever altitude you're flying over. Over water, this is less clear. And there are magnetic anomalies, but then salt water interferes. The motion of salt water causes electrical currents. This can interfere. So this is something that remains to be explored in detail. It does look promising, but we have a backup for things on the surface where we measure gravity instead. That's another way we can do position fixing. We didn't make an announcement, but there's some very exciting stuff coming very, very soon on that.
I love that idea of measuring gravity. That's pretty cool.
It's pretty awesome.
As long as you don't take it into some weird place like finding out that there are columns under the pyramids or something. As long as we don't go there.
Why not?
I do like the idea of discovering something underneath because of an anomaly. Now, this might be a silly question, but while you're flying these things around in planes and GPS is working and you know exactly where you are, can you be mapping to strengthen or bolster your data?
Absolutely.
Can you be building a better database?
That's a great question. And so you can either do this as a mission, make it your mission to go and build maps, just like Google Street Maps does, or you can do what's called incidental collection.
Yeah, that's what I was thinking. Like they're flying anyway.
Yeah, that's exactly right. And so now imagine. Maybe it's a little bit like Pokemon Go. There were all these challenges out there, but really it was an intelligence op in the background to get pictures of all these places. We anticipate that as we see broader distribution of our technology on commercial aviation platforms, on defense aviation platforms, that the end users will likely do incidental collection because they can sell it, right? The teams that are operating the aircraft or the UAVs, this is a way to make money just off the fact that they're flying. So we do believe that's going to happen, and it'll contribute to the quality of the databases.
That's great. It's amazing to think that these differences are subtle enough, but detectable enough to make that kind of impact in tracking.
I mean, I'm not a navigation expert by background. I'm a quantum physicist, and it was rather surprising to me that this was a potentially viable technology. What was super interesting, harkening back to our roots as a company, is that magnetometers that were, in air quotes, good enough, sensitive enough to measure the small variations had existed for ages, right? This was that threshold had been crossed some time ago. And so some of our peer companies said, oh, well, we're just going to use commercial off the shelf stuff. But it's not enough, right? There's a whole range of other things that matter, not just how sensitive the magnetometers are. And so we purpose-built magnetometers for this application, and we address the challenges in operation that can be addressed easily or more directly by software. So again, magnetic navigation had been around for a while. People have been doing it, and it used to be the first thing you would do is you would take off in your airplane, and then you would fly in this funny square pattern for 20 minutes. And that funny square pattern would help you calibrate an algorithm to improve your ability to pick out the signal from the noise, from the interference. But if anything changed, like you flew at a different latitude or you moved something on the airplane from one side to the other, everything broke. So imagine this, like nobody can get up from their seats, nobody can move their luggage, and when you take off, you have to fly in a square for 20 minutes. That was just a non-starter. And so we built a whole software protocol, it's called the software denoising stack, that completely throws all of that away. It does not require any pre-training. There's no like massive AI data collection in advance. It does not require online calibration. It doesn't require these special vehicle maneuvers that otherwise are mission disrupting. You just put it on and it learns what it needs to learn in real time. It takes about 5 minutes to warm up, if you will. So it's a really exciting way that AI technologies, physics-informed AI, are solving the actual problems that have prohibited this technology from being deployed in the past.
So you mentioned Lockheed Martin before.
Yep.
Definitely a dream guest for me. I really would love to get them on. I know they have like a whole quantum team.
They do. They're great.
Yeah. So I'd love to have them on. I got to believe this plus that gravity thing you hinted at. That way you're not telling me yet. I got to believe all that is of immense interest to governments, right? And defense. So is there any kind of like work going on that you're allowed to talk about or anything like that?
Sure. Space? I think, there's a number of things that we do in the public domain. We won a Defense Innovation Unit contract with Lockheed Martin earlier. I guess it was earlier this calendar year. It was announced publicly. That's focused on a new form of quantum inertial navigation, where our software is a key contributor to help stabilize these systems in the presence of noisy environments. We have a partnership in public with the UK Royal Navy through DASA, where we're doing field trials of some of our gravitational technology. We have a acknowledged partnership with the Australian Department of Defense focused on next generation quantum navigation solutions. We have a number of other defense programs that are, I'm not, for typical reasons, just can't talk about, but there is very wide interest. And since our announcement on April 14th, we're now up to almost 225 inbound customer requests for people asking to buy systems. And
that's amazing.
Among that group, and these are very big logos. I don't like not just like Joe and his dog want to buy a navigation system. We got a handful of those. Really big logos from the corporate sector, but also a wide variety of government types from NATO countries and other allies who are interested in adopting this technology. As you'd imagine, a huge amount of interest from Ukraine military about how this could support uncrewed airborne operations.
Yeah, I would think this has a lot of use in drones, in hypersonic missiles, whatever. Just anything that you have to make sure that you get to where you have to go without being detoured.
We're primarily focused right now on crewed and uncrewed aviation. So that's commercial aviation and also tactical drones. So the slightly bigger drones, not the little tiny quadcopters.
Yeah, of course. That's what I meant. I wasn't thinking of the little ones.
The price point doesn't make sense.
No,
but
it doesn't.
Still, like the devices we make are quite small. The whole thing is roughly what's the appropriate size? Think the magnetometer is the size of your pointer finger, and then the electronics that go with it are roughly the size of your mobile phone, a little bit thicker than that.
That's incredible.
It's quite small, about 15 watts, can go on a drone, not a problem. And we're very keen on deploying that for supporting our allies.
I could put it in my backpack, walk around and be like, I know exactly where I am.
We actually did that.
Oh, that's cool.
We did a walking tour around Sydney with it in a backpack before we took it out on a vehicle, and we were able to repeatedly track. In that case, you're measuring the so-called anthropogenic sources, like there's hidden underground wires or there's some underground concrete with reinforcement that's steel. That's what you measure. But if that stuff is static, then you can make a map of that, just like Google Maps has buildings on it. It's not only the natural landscape, right? So we did it. It kind of works. It's cool.
That sounds like a terrible thing to scale. Here you go, 5 million people, start walking.
Well, again, Pokemon Go was a great example of incidental collection. And if this technology keeps getting smaller, there are some reasons why it won't go infinitely small. But if it keeps getting smaller and it becomes part of a mobile phone or a laptop or whatever, just like you have a GPS receiver in your mobile phone,
quantum game,
will be incidental collection.
Yeah.
Totally
Quantum
possible.
Pokemon Go.
Yeah, exactly.
Yeah, 200 some orders. That's insane. We think of anything quantum as cloud-based mostly, and I don't think 200 of anything have ever sold in this industry because you're just accessing time. So that's pretty impressive.
It's very exciting to get that level of inbound interest, and of course now we're looking to deliver and satisfy what is very clearly a need in the sector for this kind of technology.
That's great. Yeah, I think this can have a huge impact in aerospace. I was super excited to see this because there aren't enough aerospace stories with quantum, and I do want to cover more because there's so much potential. So I'm glad you're able to come and talk about this. And before I let you go, is there one really far-reaching thing beyond that 2 years you mentioned? Is there a far-reaching thing that you can imagine sensing, like taking off in as well? Like, do you see it in astrophysics or anything, or things like LIGO, any kind of project? Is there anything that you've been thinking about, like, I wish we can get involved to improve the precision of this, Is there anything like that?
LIGO already uses squeezed light, which is pretty cool. It's for
sure.
Science experiment, not for a commercial purpose, but it's using quantum technology in a way. Look, I want to leave you with the wackiest of star shot kind of things, not just what's the next thing I want to work on. I told you before that we focus a lot on AI for quantum. And AI for quantum it's very interesting because it's a future step in the application of AI for different end uses. All the excitement that we've seen so far is basically just about chatbots, right? That's more or less all it is. Yeah. And what we're starting to see now in commercial deployment is discussion of agentic AI. So an AI agent that can do various things. Then the next step up, which we saw Jensen Huang showcase briefly, and you see Tesla doing it, is AI for physical systems, so robots. And then beyond that, we think is AI for quantum physical systems, because it's really accessing nature in a totally new way, that the machines are better at this than we are as humans. Interestingly, it's the only application where there's a flywheel effect, because if you make better quantum hardware with AI, that quantum hardware can feed back into making better AI. So the question I pose, and I posed at South by Southwest, is whether today's intelligent machines are building their future selves. Now that's some like philosophical fun, but I want to go a step further, right? Because the only area where we've seen that quantum AI really wins, where quantum machine learning is decidedly better than the alternatives, is when the data is quantum. So there was a beautiful demonstration from Google where they use qubits on their quantum processor as quantum transducers, if you will, and they feed data into a small quantum machine learning algorithm, and they showed that they can win in training. Now, that means that we need quantum sensors that quantum coherently communicate data back to quantum computers. This is like the quantum Internet of Things. And there's a huge, huge amount of work. This is not a near-term application at all. This is a long, multi-decadal vision of how advances in quantum sensing, quantum networking, quantum computing can all come together and, in a sense, be tied together by this AI infrastructure software. So we're very, very excited to be making the quantum computers better, to be making the quantum sensors better, making them smaller, making them more useful. And we're thrilled to see what our colleagues in the field are able to do on networking and applications and the like as we lift all these technologies together and we build this crazy future of quantum networked devices. Again, this is crazy. I didn't give you the pragmatic answer. I gave you the big vision, long-term one, but it is exciting.
Yeah, it makes sense. That old saying, the network is the computer. I think that's going to 100% be the statement again. Whether you're talking about interconnect, you're talking about keeping information from a quantum sensor, quantum as it returns to a quantum computer. Yeah, absolutely. That it's going to grow that way. So
yeah, it's been super exciting to see. I think in the last 2 days, IonQ has made 2 new acquisitions of small companies in support of its efforts in quantum networking. So this is definitely a growth area. We're very, very excited to see it. And
yeah, they started that a couple of years ago. Was it like Entangled Networks? I think, yeah, they did that a couple of years ago. They really believe in that for scaling. So
I think today they announced a company called LightSync, I think, that was acquired. But anyway, there are 2 announcements of acquisitions in the last couple of days. It's a very exciting domain. We're very keen to support it in the best way we can.
So it'll be great to see Q-Control literally take flight with this new offering. So congrats on that. And I hope to have you back on to fill us with some more exciting developments in the future.
Thank you so much for having me. Great to talk again.
That does it for this episode. Thanks to Michael Biercuk for joining to discuss Q-Control's latest innovation in quantum sensing. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.